What time? You know English?
Let's take down your attendance. Okay, let's start. Okay, so we are in the topic what? Topic 10, eh? Topic 10. 9, topic 9. 15 to go. We have another 6 to go. Eh? So we are halfway of discussing magnetic field. So let's recap 5 minutes what you learned so far. Okay, so F equals to BIL sin theta for a conductor, right? There is a conductor, there is a magnetic field, there is a current flow, so this is the angle between them, so BIL sin theta to be used. If it's an electron charge move in a magnetic field, and what's the formula? F equals to B QV sin theta to be used. Okay, and we found that more trouble when the charge enters in magnetic field. What type of path it takes? It takes a circular path. Okay, so what is the condition to make a circular path? What is the condition to make a circular path? The direction of motion must be perpendicular to the magnetic field. Okay, the direction of motion of the charged particle is perpendicular to the magnetic field. Then the force going to be always perpendicular to the direction of motion. So end up getting a circular path. Okay, what is the condition to have a parabolic path? What is the condition to have a parabolic path? The force must be always in one direction. Okay, circular path, the force must be always perpendicular to the direction of motion. So magnetic field, the charge move in a circular path. So therefore, what happened? The magnetic force is equals to the centripetal force. So BQV equals to mv squared over r. So we work out the radius, right? The radius found to be mb over bq. And I tell you, if you see your past year questions, a lot of things has been linked to this equation. Because as I said, very useful idea to investigate charged particle, especially in particle physics. And two particles are, the particle accelerator I told you. a certain 28 kilometer when they accelerate the particle, when they collide, they form tracks. Okay, so each track represents one tiny little particle. They want to investigate it, what charge it possesses, is it positive or negative. All done by using a magnetic field. They apply a magnetic field, they see how it deflects, okay, how it turns. Okay, the direction turns tells what is the nature of the charge, is it positive or negative, by using a Fleming left-hand rule. And the radius, the curvature, they calculate the radius. By using the radius, what they can get? They get the mass and the charge, mass per unit charge of the particle. Okay, so lots of what you call good information can be obtained about the particle by using a magnetic field. Okay, especially in the particle physics. Okay, so I think we learned up to here. Okay, today we're going to learn something new called Hall effect. Okay, maybe some of you might read about Hall effect. So Hall effect, Hall voltage. So Hall effect causes Hall voltage. Okay, this is totally new, never learned before. Okay, so a very long paragraph here. So let me draw a diagram to explain this. Okay, what is Hall voltage? Okay, so let's say you have a long thin plate. Okay, a plate which is quite thin. Okay, connected to a wire. Okay, and we apply let's say we have a battery, okay, connected to this thin plate. Okay, so let's say label it A, B, C, D, E, F, G. Okay, so inside got H now. Okay, now so the electron move from where to where? The electron will move from this way, right? Right. The electron, correct? Electron move from negative to positive. Okay, now, so electron, of course, is going to move straight because it's attracted to a positive terminal. But this situation change when you apply a magnetic field. Okay, let's say when you apply a magnetic field, you apply a magnetic field. Let's say this is your north, and down here south. You apply a magnetic field downwards. Okay, B downwards. Okay. So tell me, what will happen to the electron? We're going to experience force, right? So which direction it's going to experience force makes the electron to push which side? AE, AE, or AE the direction, or BF, AE, AE, FBI. That's a B is downward, I is downwards also. So the force is where? To the BF direction, right? FBI, FBI. Is down. Oh yeah, AE. Sorry. So AE. So what will happen to the electron? The electron which comes in. Electron which is sorry. Electron comes in. The electron will be deviated to AE. So the electron will accumulate at this side. It cannot go straight because the magnetic force pushes it to the side. So all the electron trapped to the AE. Okay, maybe not all, maybe few millions electrons which earlier comes up from the try to cross the thin plate, forced push to the side. So they just accumulated to AE. Okay. Now what happened? Because the electrons accumulated to the AE side, so here generated negatively charged region. Okay, the AE. Okay. Okay, let's say I draw like this. This is the plate. EFG. This H. Okay, the AEHD, ADH, whatever. The AEH, this region. Let me. This H, okay, the side H become negatively charged because electron accumulate there. because relative to, because this side is negative, so the other side going to be positively charged. So that means this edge going to turn to become positively charged relative to the opposite plate. Okay, so the negative positive charge induced at the side create what type of field? What field emerged? Electric field. Okay, it produces electric field. Another field was produced. Okay, the electric field, you must imagine it's a parallel plate. The plate is actually what? Vertical. Okay, it's like vertically, like there is electric field applied. Okay, this electric field is directed which direction? From the right surface to the left surface, right? Electric field. Okay, when there is electric field produced, now electron face another force, force due to electric field, right? So let's say the first 1 million electron already deviated to the right, so they sacrifice for the juniors. Okay? So the junior electron comes out. What happened? The junior electron will experience two forces, right? The magnetic force still pushing it to the right, and now you have electric force pushing which direction? Try to push the electron which direction? To the B, F, G, C, right? This direction, right? Do you agree? You see the electron is here, the electron attracted to the positive plate, right? Correct. So how many forces acting all together? You have so ignore the weight. So the magnetic force is acting this way, okay, B, and the electric force going to act this direction. Therefore, what will happen finally? The FB, when the FB is same as FE, the electrons start to move straight. Get into this wire, produces current. Okay. So temporarily, I think few milliseconds, the balancing happens. Okay? Not even few milliseconds, smaller than that. Okay, the balancing happens, and this balancing creates two fields in this thin plate. Okay, but what is the use of this? Called Hall effect. It's called Hall effect. The creation of electric field at the side and the balancing is called Hall effect. Okay, this gives us a very good application. What is the use this for us? Okay, so this create, there is a electric field, right? If you place a voltmeter across here, across the plate here, which is connected to the, like the parallel plate, right? Parallel plate you connect to the voltmeter. What happened? This give a voltage reading because it creates electric field. Electric field has a potential difference, right? So this voltage is called Hall voltage. It's called Hall voltage. A small voltage is created at the side. The voltage is not very strong, less than few millivolts, very small voltage. But this voltage is found to be proportional to the magnetic field strength. Okay, the more stronger the field, more stronger the magnetic field, more electron going to push the side. Last time, only 1 million electron push the side, create the field. Now the field is stronger. Not 1 million electron will be pushed to the side. You need like 2 million electron to be pushed to the side for the balancing to happen. So more electron accumulate to one side, the voltage get stronger. Okay, so the whole voltage is found to be proportional to magnetic field strength. Okay, so therefore this process, a new device is discovered, which used to find the strength of the magnetic field. Okay, so wherever you want to know the strength of the magnetic field of MRI, magnetic resonance imaging, they use a device called Hall probe. Okay, Hall probe, which actually the mechanism is based on this. They place the Hall probe nearby the magnetic field. The Hall probe will give a voltage reading. Okay, the voltage it gives is actually the Hall voltage. Okay, bigger the Hall voltage, more stronger the magnetic field strength. Okay, so what is the conclusion? They found that the Hall voltage is proportional to magnetic field strength. And now you think, how is proportional to magnetic field strength? Maybe it's proportional to B squared, maybe proportional to B cubed. How directly B? So this derivation, you have to know. Okay. So now we're going to discuss how they got this Hall voltage is proportional to B. Okay. Okay. In exam, this could be a one structured question. Okay. The first thing they will ask, which direction the magnetic force acting? Point, draw the arrow. So AE direction. Okay. Which edge is positively charged? Which edge is negatively charged? Which direction is the electric field strength? Okay. So this all will be like A, B, C, maybe A, B, C, part C, until part C. Okay. Until finally they will ask, okay, when balancing happens, what forces equals to what force, and so on. Okay. And finally they can tell proof that the whole voltage is proportional to the B. Okay, that's the final one. Okay, any questions? The direction where it deflect, and so on. Hope you got the idea. In exam, they might try to trick you, Cambridge. I show you the magnetic fields upwards, up to down. In exam, maybe they direct from left to right. Okay, they try to confuse you. So you have to use a Fleming left-hand rule to decide where's the electric field. Okay, it's not always up to down. Okay. Idea, initial idea. Okay, actually, this paragraph is what I've told you. Okay, so paragraph. So you can read this later. So if an electric current flows through the conductor, the magnetic field transfers force, moving charge carrier will tend to push them to one side of the conductor. This is most evident in thin flat conductor. We will discuss why it's very evident to the thin flat. Okay, that will be answered, only can be answered after the equation, derivation of the equation. Okay, why thin is best. The buildup of charge at the side conductor will balance this magnetic influence, producing a measurable voltage between the two sides of the conductor. This presence of measurable transfer voltage is called Hall effect. Okay. Okay, so yeah, the diagram I told you, this is the same diagram here. So current flowing up to down. Now with the quantity, the thickness is D, the width of the slice is W. Okay. So the current is from up to down. So FBI, Fleming left-hand rule, where the electron will be deflected, as your magnetic force is zero. Electron is moving this way, right? Up, electron moving up, current is down. So FBI is this case is diagram upwards, upwards. So current is down, it's up, FBI. So that's force. See, right, to the left. So all the electron which is coming from here going up going to be deflected to the left here. So all become negatively charged, right? So this is going to become positively charged relative to the other way. So where's your electric field? Electric field is to the left direction. So magnetic force is to the left. Electric force will be to the right? Electron attracted to the positive plate, right? So electric force is to the right, magnetic force to the left, balancing happens. So where's your voltage? The side, the H produces a Hall voltage. Okay. And now what are you going to do? How Hall voltage proportional to B? The derivation you have to know. Maybe 2 or 3 marks they'll ask. Okay. So first line you have to tell is the magnetic force is EVDB. What is it? Actually, it's actually dQE, right? dQ is E, elementary charge, Q change to E. V is the velocity. Right? In this case, VD, call it drift velocity. Right? Or current is the drift velocity. Right? So VQE actually. Right? So VD is the drift velocity. So this is the derivation. Okay, formula comes in to prove that Hall voltage directly proportional to B. Okay, so 2 or 3 marks. First line you have to introduce what is current. Current is I don't know rate of flow charge, but here what is the current formula? The next formula we use NEAVD, right? Then you have N is what? N is the charge density, right? Charge density of material. Conductors are very high, and greater charge density is the elementary charge. A is what? Cross-sectional area of the conductor. B is the green velocity. That's a current, right? That's the formula. We're going to use this to show this proof. So magnetic force is what? dQB, magnetic force. N is density of charge carriers, and A is the WB, you know that. Okay. So magnetic force is what? Okay, how they got this formula? Magnetic force is F is equals to BQV, right? BQV. BQ is, as I said, E, but the V is the drift velocity, right? Okay, but drift velocity we get it from this formula from the current. How do you write drift velocity? Make the drift velocity as the subject, so you get what? I over NEA, right? I over NEA, correct? So this leads to this equation, correct? Okay, so maybe this is 1 mark. I is NEAVD. And BQV, the V is drift velocity, so we change in terms of current. Okay. Okay, this is your magnetic force. Okay, now, and at equilibrium, the magnetic force must be same as electric force. Okay, how they got electric force this formula? How they got electric force this formula? Electric force, your early studies, electric force, what's the formula? Electric force Q times E, right? The charge times the electric field strength, right? Okay, Q here they put elementary charge as usual, E. Electric field strength, what formula in terms of voltage? Electric field strength for parallel plate. This is a parallel plate, right? The edge is like a parallel plate. So electric field strength for parallel plate is what formula? V over D, right? V over D, right? D, D. What is V? Difficult to see here. V is the whole voltage. V is the whole voltage. D is what? D is the separation of the edge. Okay, separation between the two edge which produces the electric field. The separation between the negative plate and the positive plate. Okay, you got this equation. Okay. Okay, now the above is a magnetic force, down is electric force, and in equilibrium both equate. These two equate EIB and EA. So EIB over NEA equate with plus VHE over D. Okay, we equate these two. Can you figure out how they got this finally? You see the final equation, what is missing? What has been cancelled? Here the EE cancel. EE cancel, yeah. What is not here in the last formation? What has been substituted? So this is the equation IB over NA VHE over D. What is missing here? What you have here, but not here. What has been substituted? The A, right? A has been substituted. We don't have A here. So A has been substituted with what? What is A? A is the cross-sectional area. Cross-sectional area. The cross-sectional area of the. So A has been substituted with this formula. Cross-sectional area is what? W times D. What is W? What is D? We go back to the diagram. What is W and D? Yeah. So this is W and D. W D is the cross-sectional area. The area of the thin slice. The current flow this way. This is the cross-sectional area, right? So W times D. Okay. So you go back. So here you substitute A as what? IB, and A is what? W times D is VHED. Hey, what I'm doing? Sorry, I made a mistake here. Down here is W, right? The D is W, right? W. Yeah. So D is W, yeah. Down is W. W is what? Go back to the diagram. W is the electrical formula is what? V over D, right? V over D. That D is the plate separation, right? So where's the plate here? The side plate, right? So the V over D for the electrical cell, the D must be W. Right? So the W cancel, you'll get this equation. Because you can see W cancels. Okay, 1 mark for current is MEABD, 1 mark the magnetic force, electric force formula. Okay. And in our way of deriving, the A must be substituted as WD. WD, yes, the final equation. Okay. And this final equation tells that the whole voltage is going to be proportional to magnetic strength. Okay. Stronger the magnetical, greater the whole voltage. Okay. Okay. So greater the V, greater the whole voltage. Okay, now let's discuss more about this formula. Okay, lots of questions also asked about this formula. Okay. So although VH is proportional to B, it has other quantities I over MED. Okay. The T, right? The T is actually a dimension of the conductor, which is actually dimension, right? The width, the length, and the thickness. So the D here is always parallel to the magnetic field. Okay. Go back. Remember, the D in the formula, when they give the slide, okay, thickness, width, and the length. Of course, length doesn't involve anything. The dimension which is going to be in the equation, okay, one dimension will be in the equation, will be parallel to the magnetic field. Okay, now magnetic field is vertical. The dimension going to be involved in that formula is the dimension which is parallel to the magnetic. Okay. If you give magnetic field horizontal, which dimension will be in the equation? Yeah? W. Okay. So that's another one thing you have to remember. Only dimension of that slice is the D. Okay. Because why I say in exam they're not going to label it as D. They're going to put other symbol. Okay. They try to confuse you. But remember the dimension here is the dimension of the piece which is parallel to the magnetic. Okay. Parallel to the magnetic. Okay. So now from this formula they ask why you need to use a thin slice. Can you explain? Why you need to use a thin slice, not a block? Yeah.
How did you cancel out work?
W is the thickness. W is the width.
Oh,
Width cancels. Okay, from this formula they ask why you need to use a thin slice. Thin slice to be used to get the whole voltage. Why they need to use a thin slice? Why not a block? Anybody from this formula? Why need to use a thin slice, not a block? If you use a block, what's the problem you're going to be? Anyone from this formula? Yeah? Voltage will be low for a block. Yeah, why? Because voltage is inversely proportional to the thickness. The thickness. So whole voltage itself is very low. Only little electron, only 1 million of electron diameter, the voltage is very low, millivolt. So you get to get a significant whole voltage value, the thickness must be as small as possible. Yeah. So in exam, what is it? Why you need a thin slice to detect the whole voltage? Because the whole voltage is inversely proportional to the thickness. To get a significant whole voltage, thin slice. Okay. The answer is whole voltage inversely proportional to the thickness. So to have a significant whole voltage, thin slice. Okay. All from this formula. So the scientists will make the Hall probe. You always use a thin slice. Okay. Okay. Thin slice facing the magnetic. Okay. Now another one question has been asked. The type of conductor they use, the type of the thin slice they use, made of what type of material is the best? Semiconductor or a conductor? Which is the best to be used to detect Hall voltage? A semiconductor to be used or a good conductor to be used? A copper to be used or a silicon, germanium to be used? Semiconductor. Which is best from this formula? Yeah? Good conductor to be used. Why?
better current.
Yeah? And right? When you get a significant voltage, yeah? So you want the end to be small or big? Get a significant voltage. You want the end to be very small. And is what? Charge density, number of carriers per unit volume, right? So semiconductor or conductor? Semiconductor. Semiconductor. Why? Semiconductor has a reasonably low end compared to conductor. Okay. So why semiconductor to be used to get to measure the whole voltage? What's your answer? You can say because whole voltage is inversely proportional to the charge density. So semiconductor has a low charge density compared to conductor. For semiconductor to be used. So all in this equation. Okay. Derivation you have to know. Why is semiconductor you have to know. Why is a thin slice you have to know. All explained from this model. Okay. Okay. So IB over NED. Okay, let me test. Okay. IB over NED. Okay. Okay, so you have again a slice. Okay, so this dimension is I put a different symbol. This is your A, this is your B, this is your C. Okay. Okay, so I give magnetic field this way. Okay, if a magnetic field this way, again the current is flowing this way. Okay, current coming out here. Okay. Okay, just now, what's the formula for all voltage you got? VH equals to what? IB over NED, right? Yeah, VH, IB over NED. For any type of setup, the I doesn't change, the symbol B doesn't change, N is the charge density doesn't change, E is the material charge density, the D, the symbol D has been changed. In this case, which represents the D here? A, C, B. Is supposed to be replacing the D here. For this diagram, should be A. Should be A. So for this diagram, the VH must be what? IB over NEA. Should be A, right? So that's why I say the dimension in the equation is parallel to the magnetic. And it is horizontal. Dimension is supposed to use in the formula is the one A. Okay. Okay, maybe so. Yeah, this is you got lots of animation. So you apply a battery. So electron moving that way. So they are moving straight, not disturbed by any field. Okay. So when suddenly what happened? We apply a magnetic field. We apply a magnetic field, the electron was upwards. So create what? Create a electric field which direction? Right, electric field up and down, so that the electric force is very force upwards, the electron starting. The C is all stuck there. So create the electric field. So where's your direction of the how do you put the voltmeter to measure the whole voltage? Up and down, right? Across here. So in this case, okay. Yep.
Is this correct? The current is so the
That one. Current is downwards.
towards this.
That would be C is down. F I is down. Oh yeah. This way.
So the electrons are both
This this is the direction of electron, right? Current is this way.
is that from negative?
Negative to positive is electron. Current is positive to negative.
Isn't the current more electrons?
Current is positive to negative. Electron is negative to positive. But in your Fleming left-hand rule, the direction you point is the current. So current in this case is upwards. Because current always flow from positive to negative. Okay. So because current is upward, negative will down, the force will be to the left. So the electron will push to the left.
No, I did it myself.
See, how come the negative is like opposite direction?
How come the
It's the opposite direction of the
force?
Negative is for positive. That's like
Here
the force is like this way, which is
oh, here because electron moving to the right, current is to the left.
He was there. I was like, really angry about it. Because they were doing the last pages, they end up the didn't want to like answer. They wanted to like
Yes, so that's one of the use to find the all voltage. All voltage is used to find the magnetic field strength. Okay, magnetic field strength found to be proportional to the whole voltage is proportional to the magnetic field strength. But when you use a Hall probe, the device connected down there is a voltmeter. It's a voltmeter. So you go to the nearest MRI, which gives 3 Tesla. The voltmeter reads voltage. Okay? So you won't get Tesla. So let's say you go to MRI, it gives you 6 volt, 6 millivolt. Let's say. Go to the MRI, it gives 6 millivolts. But it's 3 Tesla actually. You don't magnetical 3 Tesla, you go nearby, 6 millivolt. Okay? You go and bring this Hall probe nearby to unknown magnetic field. It shows 2 millivolts. So what is the strength of that field? 3 Tesla, 6 millivolts. This unknown magnetic field shows 2 millivolts. So what is the strength of this magnetic field? Pole voltage proportional to magnetic field strength. Right? 6 millivolts, 3 Tesla. 2 millivolts, 1 Tesla. 1 Tesla. Based on what? Pole voltage proportional to magnetic field strength. So don't worry, the Hall probe is voltmeter, but before you use the Hall probe, you must calibrate the Hall probe. Okay? Very important for design experimental data. If design experiment come out is a magnetic, something to do with magnet, so you have to use Hall probe. Okay? When you explain, Hall probe is used to measure magnetic field strength, you get 1 mark. But if you say use a calibrated Hall probe to measure the magnetic field strength, you get 2 marks. Okay? So you must say the Hall probe need to be calibrated. How do you calibrate the Hall probe? Bring this Hall probe to the known magnetic field strength. Check how many volts. And okay, that's one use. Another one important use of this effect. Okay. This electric field and magnetic field application. It's called for something called velocity selector. How many of you taking chemistry? Majority of you. Only 5. Okay, chemistry you learn mass spectrometer. What is the function of mass spectrometer? Long time ago. Find the isotopes. Find how many isotopes the solution contains, right? You get the pitch, right? Yeah. So actually isotopes what? As the same, what is isotope? Same nucleon number, sorry, same proton number but different nucleon number. So the charge of all of them is the same, but they are different mass, right? Different mass. So mass spectrometer, you have mass spectrometer design. You have, but theoretically you saw in the YouTube mass spectrometer. Okay, mass spectrometer in physics, what we're going to talk about mass spectrometer here is how mass spectrometer works. What is actually using inside to get that isotope. Actually uses magnetic field and electric field. Mass spectrometer. Okay. Mass spectrometer, the complete diagram is this. This is a mass spectrometer. This is a complete setup of mass spectrometer. You will apply a solution, what we call the solution here, which contains few isotopes, 1 or 2, 3 isotopes. Okay, charged, accelerated by using electron gun, pass through this region. This is called velocity selector. Our focus in physics discussion is about this component, velocity selector. Because velocity selector means they want to know what speed the charged particles enter the mass spectrometer. The speed it travels is quite fast. Okay, the speed, how to get that speed of the uncharged particle, which is very tiny little charged particle moving quite fast. Do we have any device to measure it? We can't use light gauge, we can't use stopwatch moving very fast. Right? So what we use? We use a electric field and magnetic field to find what speed it's traveling. Okay, it's called velocity selector. After that, we have some region to reflect. Now, current syllabus, this discussion has been removed from your syllabus. So they only focus on this. I focus on this velocity selector. How they get to know the speed the charged particle is traveling. Okay. So for that, I go back to the early slide. So this is only that component. It was horizontal, but actually vertical. Okay, when a charged particle get into this tunnel, okay, a magnetic field is applied and also electric field is applied. Magnetic field is crossed into the page, so the charged particle experience magnetic force which direction? positive charge, let's say, moving to the right, magnetic field into the page. So magnetic force is upwards and upwards. Okay, so magnetic force is upwards. So the charge will deflect up, right? So they can see the charge is deflecting up. So what they do? They apply a electric field. Okay? They apply electric field such a way that the charged particle move straight. Okay? So which direction the electric field need to be applied? The electric field must be applied such a way that the electric force is which direction? Downwards, right? Magnetic force is upwards. So we try to counteract that magnetic force. So the electric field must be applied such that the electric force is opposite to the magnetic force, right? So the electric force will be QE downwards. So to get downwards, because of positive charge, upper plate must be positive, right? Down is negative. So the electric field downwards. So positive charge will experience a force towards the negative field, right? Downwards. So they adjust the voltage of the electric field until the beam comes up from the tunnel, straight. The beam comes up from the tunnel, so they know. So the magnetic force is equal to the electric force. Okay. So what is the purpose we are doing this? We want to find what? We want to find what speed this charged particle enters this tunnel. So how they got the speed? They know the force is the same. BQE is same as QE. There you got the velocity. So BQE same as QE. You get the velocity is E over B. Okay. So the speed the particle enters the tunnel is the electric distance divided by the magnetic distance. Get the speed. Okay. So one easier way to find what speed a charged particle is traveling. Okay. E over B. This device called velocity selector. Call it velocity selector. It's one component of the mass spectrometer. Okay. So E over B, E no V over D, right? V potential difference over the plate separation, and D. You can find the what I call the speed. Okay, again, this also they ask many times. As usual, sometimes they change this positive to negative. Sometimes instead of magnetic field into the page, they give out of the page. Okay, and they will ask which direction, which plate is positively charged, which direction is the electric force. All the kind of questions comes in. Let's say this is a negative charge. This is a negative charge. What changed? Do you need to change the direction of the magnetic field? No need, right? If it's a negative charge, what changed? Magnetic force now, up or down? It is a negative charge. The magnetic force will be downwards. How about electric force? Negative charge. Negative charge. Electric force upwards. So the force will be opposite, the other way around. So do you need to change the polarity of the magnetic field, electric field if it's a negative charge? No need. So this big one, we need to change the polarity. With a positive or negative charge, you can use this setup. So because the force going to always oppositely directed. Okay. So now just we go a little mass spectrometer. I can't trust Cambridge, although they remove it, they will ask go a little out of the box. Okay. So let's discuss this last a little. So this the solution made of let's say 3 isotopes. 3 isotopes enters here. Isotopes have 3 different masses but same charge. Because charge is the same but different masses, because they are pushed by the what you call same electron gun. What is electron gun, right? Electron gun. Where do you have electron gun? CRO has electron gun, right? Cathode ray oscilloscope. What is electron gun? You have a metal plate. Hit the metal plate, you got free electrons. Then the free electrons don't know where to go, but it has some kinetic energy. We have a potential difference. Pull the electron to one side. Okay. So we make this as a positive plate or negative plate. Make it as a positive. We give a very high voltage. We give more higher voltage. The electron will move to this side with high kinetic energy. It's called electron gun. To accelerate the charged particle to one direction. Okay. So that happens here. Electron. So the electron, when the isotope comes out, all of them have the same velocity, but they have different momentum, of course, different mass. So here, all of them will move in a straight line, all isotope. But when you come to the second region, now you get 3, 5, or 4, 5, right? The isotope, in the mass spectrometer image. Why is it got 3 or 4 spikes? Because they use another magnetic field. They use another magnetic field. When the charged particle enters here, the 3 isotopes, only magnetic field is applied here. And only magnetic field applied, what will happen to the 3 isotopes which has a different mass? They move in which path? They make a circular path, right? Because magnetic field, charged particle have to go for a circular path. Not complete, maybe part of the circular path. So all the isotopes make a circular path. Same radius? No, different radius, right? All of them make a different radius. Why they make a different radius? What's the formula for radius? What equals to what? Yeah. What equals to what to find the radius? What force equals to what force? The magnetic force equals to centrifugal force, right? It's moving in a circular path. So BQV equals to mv squared over r again. We get the radius formula, you know. So the radius formula is what? mv over bq, right? Earlier we did that. So mv over bq, right? I go back, the whole story, Yeah. The radius formula, right? So you see this formula, the 3 isotopes, all of them have the same charge. Okay, they expose to the same magnetic field. All of them have the same speed, but all 3 have a different mass. So which one make a big radius? The more massive isotope will make a bigger radius, right? B same, Q same. So what will happen? So if you got 2 isotopes, 2 R1, R2. The R2 more massive or R1 more massive? Because R2 is more massive, right? And big radius. So you get this photographic clip. So you get the spike. Now digital. The 3 spike means they make 3 different radius. Okay? So you get that isotope. Right? So mass spectrometer works based on which field? This is 2 different magnetic fields. One here, another one here, different strength. But they also use electric field to find the velocity. Okay, velocity. Your syllabus focus to velocity. Okay. Okay, so for time being we stop here. Yeah. So what is it today? All effect and velocity selector. Okay. Any questions? No questions, Okay.
This